computer?
Yeah.
Yeah.
Okay.
Okay, good. And so we're going to ask people, given that size, we're going to ask people to mute themselves, or we'll keep people muted, and to post any questions that you have in the chat. We'll have the talk will go for about an hour, and then we'll have plenty of time for questions. And Stefan has agreed to stay on if people want to have a smaller conversation after the more formal give and take. So I'm excited today to introduce my colleague, Stefan Sommer, who's going to talk to us today about the climate problem. Science communicator, film producer, author, and public speaker. Stefan is a founding board member and speaker for the Northern Arizona Climate Change Alliance. He's an affiliate with NAU's Department of Biological Sciences and Center for Adaptable Western Landscapes, with expertise in community ecology, sustainability, climate change, and education outreach. Stefan writes for the Arizona Daily Sun as author and editor of the column Spotlight on Climate, and he served as executive producer of 4 award-winning PBS documentaries on biodiversity and habitat conservation. So, Stefan, thank you so much for speaking with us this afternoon, and I'll turn the Zoom over to you.
Francis, thank you very, very much. And thank you all for coming today to spend some time to get our heads around what science tells us about climate. We know climate change is an existential issue that has reached global proportions. And we're going to talk today a little bit about not only what science understands, but what are the already ongoing consequences and how might those play out further in the near future. As Francis said, please put questions that you have into the chat, and Francis, as moderator, will bring those questions forward so that we don't interfere with one another's audio. And I will be sharing a PowerPoint, which, let me get that up and started here. Okay. As Dr. Reamer was saying, I'm Stefan Sommer. I've been recently retired professor from NAU, and I serve on the board of the Northern Arizona Climate Change Alliance, and as such, do some community organizing, but also make these kinds of presentations. My goal is to help people understand what science knows about climate change. And part of my reason in this is I think some of you will already know some of the things that I'm going to present about climate change, yet I want to refresh everybody's understanding of those things, because we are in such a desperate situation. We need everybody now to be climate ambassadors, if you will, to be able to reach out to your family, your friends, and everybody you know in every way you can to get them to not only understand about climate change, but activate them to do something about climate change. And that's really what we're all about at NASCA, the Northern Arizona Climate Change Alliance. We are here to inform, engage, and empower people to do something about climate. So I like these 2 pictures as an introduction. We are putting out lots of greenhouse gases into our atmosphere, and as a result, we're putting energy into the atmospheric system with the outcome of more extreme weather of all sorts. Before we get going, I'd like y'all just to think for a moment. How do you know the things that you know? Where has your understanding of the world come from? Well, as my image here suggests, we're a social species. So we get most of our understanding of the world around us through social interaction, in school, media, through faith organizations, and our whole social network. And then, if we've had good schooling, then we can also observe the world and interpret what we observe to, and through reasoning, understand how the world works around us. But we're a social species, and now we've got social media, and we've got the internet, and we've got all sorts of sources of information and misinformation. So it gets harder and harder for us to weed through to what is really true. And so I would suggest that the way through this difficulty is for us to focus on critical thinking and data. So what does the data tell us about climate change? Well, there's just no question. If you look at the record, this is from 1880 to 2016. The global average temperature has been rising steadily and very rapidly compared to anything we've seen in nature in the past 300 million years. And I'll show you the data on all of that. So there's no question that climate change is happening, and you may see things in social media and on the internet that suggest otherwise, but what I'm going to present to you today is the scientific understanding of climate change. And here's a more thorough rendition of that data. In this first graph is the last 2020 years from 0 AD up to present, and you can see that temperatures have changed dramatically in about the last 120 years, perhaps. Really, the main transition has started back around 1960s. And you can see that the way these temperature data are often presented is they take the long-term average and call that zero. And so this is called temperature anomalies from that long-term average. And all the blues and greens down here are where the temperature was lower than that long-term average. And all the yellows, oranges, and reds up here are where the temperature is higher than that long-term average. So there's no question that the globe is warming. And we can see that in a wide variety of different ways. If you don't like data and all of that stuff, this visual really sums it up. This is what's been happening to Arctic sea ice since about 1980. And of course, every year it expands and contracts, but the overall extent of sea ice has been contracting more than it's been expanding. And this is good for folks who are looking for commercial shipping lanes. It opens up commercial shipping lanes, but it's not good for any organism that depends on that ice. And it's certainly not good for the Earth's average temperature. So polar bears are being driven towards extinction because they're losing their hunting habitat, which is that ice. Okay. And I know you all have heard about the greenhouse effect. You might not know that it was first proposed by Joseph Fourier in 1824. So we've known about the greenhouse effect for a long time. And the explanation, what he was looking at was the heat budget for the planet relative to our distance from the sun and the amount of heat energy we were getting from the sun. And he realized that the Earth is warmer than it should be, just based on what's coming in from the sun. And he proposed that there were things in our atmosphere that were trapping some of that heat in. And in fact, we've since discovered exactly what those are. They're the things that we now call greenhouse gases. So we get lots of different radiation from the sun, mostly in shorter wavelengths. When it reaches an object on the surface of the Earth, that object warms up. We've all experienced this by standing in the sun and feeling warmer. Warm objects re-radiate heat energy towards colder objects. So all of these warmed up objects on the surface of the Earth are re-radiating heat energy towards outer space on average. And the wavelengths of that radiation shift to slightly longer. So what we're radiating back towards outer space is infrared radiation, thermal radiation, heat radiation. And it's the greenhouse gases that block that radiation from reaching outer space because they absorb those particular wavelengths. So what we're doing with greenhouse gases, basically, and the greenhouse gases are similar to having a blanket on at night. That blanket keeps the heat that your body is radiating from escaping very far from you, and it keeps you warm because it keeps that heat in close. So when we add greenhouse gases to the atmosphere, basically what we're doing is we are thickening that blanket and holding in more heat. We can look at the effects of that greenhouse effect over long periods of time. One way that scientists do this is by looking at ice cores from Antarctica. And here's a picture of an ice core. You can kind of see there are small striations throughout that. And each of those striations is a layer of snow that fell millennia ago and was compressed into ice. In that ice, we have a record of many different things, but a couple of them are very important for understanding climate. One is there are little gas bubbles in that ice that were frozen solid since the time that that became ice. And so we can look at what was the atmospheric composition at the time that that ice froze. And so we can get a measure of the concentration of CO2 in the atmosphere from those little bubbles. We can also look at the relative amounts of heavy water and normal water. And if you don't know what the difference between those is, basically, different elements have isotopes, and hydrogen has an isotope that weighs twice as much because it has a neutron in its nucleus. We refer to that as deuterium. Oxygen has a heavier isotope, 18, because it has 2 extra neutrons in its nucleus. In any case, small proportions of hydrogen and oxygen in the world are these heavier isotopes of those elements. When they combine to form water, H2O, when you have one of those heavier isotopes, that water is heavier. What's the significance of all of that? Well, because those water molecules that are heavier are harder to evaporate, it takes a little bit more energy to evaporate them from the surface of the ocean. When the Earth's temperature is higher, a higher proportion of the heavy water is evaporated into the atmosphere. And then it goes into the atmosphere, it forms clouds. Those clouds go over Antarctica, drop snow. That snow has if the surface temperature of the oceans is higher, that snow that results will have a higher proportion of heavy water in it. So the proportion of heavy water tells us what temperature the surface of the ocean was at the time that that snow formed. So hopefully that all makes sense. So again, we've got over all these years, we've got a record of atmospheric composition from the ice bubbles and record of the Earth's average temperature from the proportion of heavy water to normal water. This is the Vostok station on Antarctica, and you can see they've cored down to 420,000 years of ice, layer upon layer. And the layers that are higher toward the surface are the younger ones. The oldest are down at the bottom. So we've got a regular record of all those things: oxygen, heavy water, and temperature in that record of ice. Now, I'm not going to show you the whole 420,000 years here, but let me show you the results from the last 160,000 years of ice. And it's this. On this graph right here where I'm showing, that's present, year zero, and 160,000 years ago. So we're going backwards through time here. And from those gas bubbles, we know the CO2 concentration in the atmosphere. From the proportion of heavy to normal water, we know the Earth's average temperature at that time. And so over these 160,000 years, we can see that there's a high correspondence between CO2 concentration in the atmosphere and the Earth's temperature. CO2 concentration goes up and temperature comes up. CO2 concentration comes down and temperature comes down. There's not a 100% correlation between those two, but the correspondence is very high. So this is one of the many kinds of evidence that the scientific community looks at to understand the relationship between CO2 concentration in the atmosphere and the Earth's average temperature. And there's just no question that the two things are related. Here's what we've been doing to CO2 concentrations just since 1960. Back prior to the Industrial Revolution, the atmospheric composition of CO2 was about 280 parts per million. And as of today, we are just over 419 parts per million. Since 1960, this is the change. And that's a huge amount of change. Anybody know what the little red oscillation might be in this graph? Well, if you've thought about this before, you probably quickly come to the realization that what that is the annual variation of the seasons. Because life is carbon-based. When photosynthesis occurs, CO2 is a raw material. Photosynthesis takes CO2 out of the atmosphere. When we take the product of photosynthesis and burn it physiologically and respire, we release CO2 into the atmosphere. And so what this little red oscillation is the annual fluctuation in CO2 in the Northern Hemisphere, since this is all recorded out on Mauna Loa, and there's relatively little mixing of the Northern Hemisphere and the Southern Hemisphere atmospheres across the equator. So which season would it be when CO2 is peaking in these little red oscillations? CO2 goes up if there's more respiration. And so there would be relatively more respiration in the winter and relatively more photosynthesis during the summer. So the peaks of that oscillation are winter and the troughs are summer. But think about this. The magnitude of that red oscillation, from a biologist perspective, that's a huge change in CO2 concentration because it measures the relative proportion of respiration and photosynthesis for all life in the Northern Hemisphere. Now compare that magnitude of the red oscillation with what we've done since just 1960. We have thrown this system into a whole new state of being.
Stefan, we have a question, maybe it's a short answer for now.
Yeah.
What was happening on Earth 140,000 years ago when our measures looked a lot like they do today? What brought Earth back from that brink? I think an important question that climate deniers often pose.
An important question. And so if you notice, back then it was about 280 parts per million. There are a whole slew of different reasons why it was declining, and largely, well, yeah, no, that's not true. So basically this last rise, it was when we were coming out of the last ice age. There are a lot of reasons here, and it's not a short answer. So I won't get into that whole thing, also partly because it's not my area of expertise. But yeah, the background level of CO2 in the atmosphere of 280 parts per million occurred back here from 140 to 120,000 years ago, and was again the case right before the Industrial Revolution. Yeah, we could spend a whole nother hour talking about all of the reasons for that shift. But back around 1880, we started rising primarily because of human combustion of fossil fuels. And if you look at records since we've had instruments to measure these things, from 1880 to 2021, not only has the carbon dioxide risen steadily in this lime green line, but it's corresponded again pretty closely with CO2 concentration. We have now warmed the Earth by about 1.3 centigrade degrees above that normal background temperature, and that's equivalent to 2.3 Fahrenheit degrees. Here's looking at that record over the last 1,700 years. And you can see there's variation in the Earth's average temperature. It's variation since this, remember, this is the long-term average, basically up to a half a degree higher than that average and a half a degree lower than that average. We were going through, from 1200 forward, we were going through a period of cooling. And then more recently, in the last 100 years, as I was saying, we are seeing a very rapid rise in the Earth's average temperature. From this graph, you can see over a slightly longer period of time. So this is the last 20,000 years. And here we were coming out of the last ice age to a warmer time. And then for the last 5,000 or 6,000 years, we have had a slight cooling trend on Earth that has just in the last 100 years been reversed dramatically. So we've looked at this change at various time scales. And how are we changing the atmospheric composition of CO2? Well, primarily through the combustion of fossil fuels. If you look, this is a broken histogram bar. So over 5,600 teragrams of CO2 have been released by human beings just through the combustion of fossil fuels. We also use fossil fuels for a lot of other non-combustion purposes that also release CO2 into the atmosphere. Iron and steel production, cement manufacture releases a lot of CO2. This is just a compilation of various industrial sources of CO2. But certainly our entire CO2 footprint is not just the industrial footprint. If you look at this graph, it's a little bit more inclusive. So our energy production is a big source of our CO2 emissions. That's primarily the combustion of fossil fuels to produce electricity. We use fossil fuels in all sorts of other ways: residential, commercial, transportation. Our waste releases a good bit of CO2 and other greenhouse gases for that matter. But I want to point out that about 30% of our overall emissions comes from land use. Why would that be? Well, if you think about it for a minute, if we burn the rainforest, that's kind of an obvious source. You burn that forest and it releases a lot of CO2. But the part that maybe most people don't think about is that when we till soil, soils are a huge repository of decaying carbon materials. When we till that soil, we mix in oxygen and we greatly speed up the decomposition of that carbon that's in the soil. And so that releases a very large amount of our emissions into the atmosphere. So our various land uses also are a source beyond just the combustion of fossil fuels. Back in 2018, the Intergovernmental Panel on Climate Change reported that we were producing over 40 gigatons of CO2 emissions per year. And in 2020, it was over 59 gigatons of CO2 per year. I think some of that huge increase is because we got better at measuring our carbon emissions. But nonetheless, our carbon emissions are continuing to increase, and we need to do the opposite.
Stefan, there's a question about plastic production. Does
Yes.
plastic production play a part here?
Plastic production, yes, there are some carbon emissions, but the primary problem with plastic is that it fouls the oceans and fouls various habitats and, chokes organisms and does all these kinds of bad things. Its carbon footprint isn't the worst thing about plastic production. If you think about it, really, the plastic that doesn't degrade becomes a repository of carbon that, if we protected it and kept it from breaking down in sunlight and so forth, or if we protect it from burning, it would hold on to that CO2, that carbon, for a long time. So plastics production does have some emissions, but the primary problem with plastic productions is pollution of various sorts. I'm talking primarily about CO2, but so I wanted to make sure that everybody is on the same page with me. CO2 is not the only greenhouse gas that we emit. Methane is a much stronger greenhouse gas. The reason we talk about CO2 more than methane is just because we produce so much CO2 and relatively less methane. Although, if we thaw the permafrost, then our production of methane will start to skyrocket. And anyway, nitrous oxide and CFCs and other things that we produce are also greenhouse gases. I want to spend a little bit of time on this, because what this looks at is how the Earth's temperature has changed over long periods of time in the past. This first graph shows from the present at 0 to 300 million years ago. And Earth's average temperature changed in a pattern that looks about like this across a 10-degree centigrade scale of variation. And this corresponds with the shift in the tectonic plates and the change in ocean circulation patterns, because that has a big effect on how the Earth stores heat energy. And so over that longer period of time, we have seen a pretty dramatic change in the Earth's average temperature. If you expand out just the last 3 million years of that 300 million, you can see this pattern of Earth's temperature variation across a 6-degree centigrade scale of variation. And you can see some very regular patterns there. Why is there that regular oscillation? Well, this is what we refer to as the Milankovitch cycle, and it's a compilation of all the different orbital cycles. The cycle of the eccentricity of the Earth's orbit around the sun, the cycle of the tilt of the Earth's axis relative to that plane of orbiting the sun. All of those, and sunspot cycles, which only have an 11-year cycle, also are in that Milankovitch calculation. So generally speaking, we get this major swing every 40,000 years or so. And that's all due to orbital. So we refer to these different things, the tectonic shifts and the changes in our orbit around the sun, as natural forcing factors. I don't know why the climate scientists call them forcing factors per se, but what they're doing is they force the Earth's average temperature in one direction or another. So tectonic shifts, orbital changes summed up in these Milankovitch cycles, and other smaller scale things like volcanic eruptions can be forcing factors that change the Earth's average temperature. If we expand out the last 50,000 years of that 3 million years, that's here, again, across a 6-degree centigrade scale of variation, you can see that there's smaller variation, and then we came out of the last ice age. That's right about here. And so that's due to a change in the Earth's orbit around the sun. So we have been in a relatively warm period of time between ice ages. And then if we look at just the last 1,000 years, you can see that we got much smaller scale variation just across a 1-degree centigrade scale of variation. And these are due to various things, including major volcanic eruptions. All of those volcanic eruptions, orbital, tectonic, forcing factors are all natural forcing factors that change the Earth's average temperature. I'm spending a little bit of time on this because in the next graph, I want to show you the relative effect of those natural forcing factors relative to anthropogenic or human-caused forcing factors, such as the greenhouse gases. Also, we also affect this by changing the reflectivity of the Earth's surface. So if we take a natural habitat and turn it into a parking lot, the reflectivity, the albedo of that surface area changes. So that's another way in which we have human-caused forcing factors on the climate. So this is from the 2007 Intergovernmental Panel on Climate Change report. They did the same analysis back in the 90s, but they had a much better graph in 2007. So I'm showing you that one. And what this is in both of these graphs, the black line is the actual temperature record. Okay. And then what climate scientists do is they put together models to try to understand how different variables affect climate, and in this case, specifically Earth's average temperature. And they put together this model with all of the natural forcing factors and the anthropogenic or human-caused forcing factors in the model. And then they ran the model over the last 100 years, 120 years now, and it tracked the actual temperature record pretty closely. That's one way you can test your model. Does it predict what we already know to have taken place? And they concluded based on this, that yes, this is a good, accurate model because it reflects the actual changes that we've seen in the past. Then they ran the same model, but took the anthropogenic forcing factors out. That is, our change in the greenhouse gas concentrations, our change to the albedo of the Earth's surface. They took those forcing factors out, and here's what the model output was then. It suggested that we would not be seeing this warming that we saw since the 1960s, but instead, without those anthropogenic forcing factors, we would be seeing a steady or slightly cooling Earth's average temperature. This is the smoking gun. This is the one that says current climate change is caused by human activity, period, amen. And I hope you all can understand that there are lots of ways that scientists look at this, but really this is the cause and effect smoking gun. Oh, I should point out that some of these drops are due to large volcanic eruptions that are named here on the graph, Pinatubo, and so forth. And basically what volcanic eruptions do is they put a lot of dust and aerosols into the upper atmosphere, and that blocks incoming sunlight. So they initially, for the first 3 years or so, they cool the Earth's average temperature, but then they're also adding greenhouse gases. So in the long run, they also increase the Earth's average temperature. And this graph just basically shows how the temperature has changed since 1850 to 2016. Each turn around the circle here is a year, and you can see the months around the outside. And I want you to see two things in this. One, as it goes around, it keeps expanding. So that means the temperature keeps rising, but also that the rate of temperature rise keeps increasing. We'll let it run one more time. So that's what we've done so far. And for Flagstaff, for those of you who are from northern Arizona, here's what the temperature record had been up to about 2017 or so. This analysis was done when we put the Flagstaff Climate Action and Adaptation Plan together. And then they projected from there. And basically, the projections suggest the same thing will happen here as in the rest of the world. We'll see ongoing increases in temperature if we continue with business as usual emissions, that is RCP 8.5, the higher emissions scenario. Then we can expect about a 10 degrees Fahrenheit rise by the year 2100. And in Flagstaff, for us, the main thing that's changing our average temperature is the loss of low temperatures. The average keeps increasing because we're losing our lowest temperatures, meaning that when we do get snow, it won't last as long. Precipitation is a little bit harder to predict because, for one thing, as temperatures rise, warm air holds more water than cold air. And again, we're putting more energy into the atmosphere, so it has stronger winds, stronger storms. We can expect more intense rainfalls, but they might be more sporadic. So the outcome with rainfall, precipitation in general, is a little bit more difficult to project, but we're going to spend a little bit of time talking about that. So basically, what have we done to our climate? In a nutshell, we've been adding energy, heat energy, to the atmosphere and the land surfaces and the oceans. And what do we expect as the outcome? We expect more extreme weather. If you don't remember any of the data that I show you, I don't have this picture of the globe upside down for any political reason. I have it in this orientation so that y'all can see old man wind. I don't know if y'all can see it now, but there's an eyeball, eye, nose, howling beard, wisp of hair. This is old man wind, and we are just giving old man wind that much more power to howl up a storm. You don't remember the data, remember old man wind. This is the most commonly used picture of the Earth from space, so you might recognize it based on seeing old man wind in the future. And in fact, the data show the same thing. So we are seeing increased numbers of floods, numbers of storms, and numbers of droughts. The only reason that the numbers of droughts look lower is because how do you count a drought? Well, it might be the entire north of Africa that is in a drought, but it still only counts as one. Okay, but droughts, storms, and floods have all been increasing. What are the effects of these changes? Well, so we'll talk a little bit about rising storm frequency and intensity. We're going to talk about this effect on water and fire frequency. We'll talk about the effect on biological species, biodiversity. I think we're going to have to skip the ocean stuff, but then we'll talk about some human impacts. Okay. So increasing frequency of storms. There's just no question that we're seeing more storms. This is for North Atlantic tropical storms. So the frequency has increased quite a bit. We've seen the outcome of those. For those of you who remember Hurricane Katrina in 2005, it killed almost 2,000 folks and displaced over 400,000, cost $161 billion, single storm. Sandy, 2012, killed 233, displaced 750,000 folks and cost $71 billion. Hurricane Harvey, 2017, killed 107, displaced 30,000 and cost $125 billion. Hurricane Maria, same year, killed over 3,000 folks, displaced over 130,000 and cost $90 billion. Now we're in the middle of Hurricane Idalia, and the number of deaths, number displaced, and the costs are still pending. So we can continue to see increase storm frequency as well as intensity. This is just to give you an idea. So those folks who were hit by Maria in Puerto Rico fled to the upper United States. And these are the locations from which those refugees filed FEMA relief applications. So it gives you an idea of where those climate refugees went, at least in the short term. This is a map of damages from various climate-related disasters. And you can see that hurricanes play a big part in that. Flooding and wildfires in the West have also been increasing. We'll look at that data in just a minute, but the numbers there don't quite compare with those from hurricanes and other large storms. Tornadoes have been increasing. It's not just the hurricanes and tropical storms, but this is United States, January to December. That's the whole year. Number of tornadoes have been rising steadily. And the power of those tornadoes has been increasing. I don't know how many of y'all remember Joplin, Missouri. It was one of the first tornadoes that kind of had hurricane power. It had a 2-mile wide swath, took out cement buildings in addition to just wood structures. So we can expect that to continue to intensify. In 2017 alone, these kinds of climate disasters cost folks in the United States over $306 billion. So these damages are becoming very real. If you look at the projections for us in the Western United States, this is for California and this is for the Great Basin. Just as everywhere else, average temperatures keeping on rising. But for precipitation, the main projection isn't that the average amount of rainfall and snow is going to change much, but that the variation is going to increase. So if you look at this, actual historical records versus the projections, which are in green and orange, you can see that if you think of this as a caterpillar, the fuzziness of the caterpillar is expected to increase. That is, more of that variation in precipitation. Same thing for the Great Basin. The fuzziness of that caterpillar is expected to increase. And so we expect greater and greater variability in precipitation. It's harder to say whether it'll be more or less, but always more variation. And California has been seeing this. This is Lake Oroville, which is a reservoir lake. That's the Oroville Dam down there in 2015. Just 17 months later, it was so full that it was overflowing and some damage in the spillway was threatening to undercut the whole mine. Just 14 months later, so intense period of rainfall. And they were evacuating people in this whole region below the dam because they said, if this breaks, all of these folks are in danger of getting their homes flooded. And I think that was over 200,000 people they evacuated from this region. The dam didn't breach, fortunately, so people could go back home. So regional fires are also getting larger and more frequent. This shows you the area burned from 1984 to 2010 across the Western United States, and you can see that it's a huge portion of our forested land. If temperatures increase by 1 degree centigrade above and beyond this, the projections are for fires to increase by 380% in Arizona and New Mexico alone. These are projections from 2011, so I'm sure there are more updated projections at this point. But wildfires across time. This is for the Western United States. And you can see that there's just no question that the frequency of fires has been increasing, in addition to the last couple graphs, which showed you that the size of fires has been increasing. And I don't know if you all remember these headlines from 2015, but this is from the Daily Sun. They were running out of firefighters. They did not have enough fire crews to even go to all the fires at that time. This is where I grew up in Bishop, California, just outside of Bishop, California, the Round Valley Fire. When I was a kid in this region, this was known as the asbestos forest because it was primarily piñon juniper scattered across a big landscape. And so there wasn't really the possibility for a big forest fire. In 2015, that was proved wrong. No longer the asbestos forest. This is Flagstaff in 2010, the Schultz fire. And we are still suffering the consequences of the Schultz fire because of flooding and erosion. This was some of the flooding at the time. So you remove the vegetation from a landscape and its ability to hold rainfall greatly decreases, and you can get massive flooding. And we've seen that again and again with various fire scars and then intense monsoon downpours here in Flagstaff. The overall cost, flood and restoration costs $130 million. So again, for a community our size, these are real dollars. Fortunately, there were federal dollars that could help us with that because our community probably could not have absorbed these kinds of costs. In addition to those increasing storm frequency and wildfires and so forth, we are also affecting all the species that make up our life support systems. I don't know if you, for those of you who know that the life zones of the earth were defined here in Flagstaff by C. Hart Merriam back in 1898. He did vegetation surveys from the top of the peaks down to the bottom of the Grand Canyon, and he defined all these life zones. Each life zone has plant and animal species in it that are adapted to the conditions of that elevation on the mountainside. We now know that as things are warming up, species from this life zone are fleeing up the mountainside into this life zone, and those are fleeing to that and so forth. And the ones that already were in the life zone at the top of the mountain, they're just out of luck. They've no longer got the habitat they need. For those species that don't live on mountainsides, they've got to go much further distances to stay within their range of living conditions. And so we'll talk about the northward push that species are experiencing as well. So the escalator effect that is being pushed up the mountainside is being documented in species after species, and here are just a few examples. Oftentimes it has to do with just change in habitat. So the ptarmigan is affected by lack of its food species, its plant food and insect food, and lack of camouflage. It's changing its color from white to camouflage at the wrong time of the season relative to when snow is covering the ground. So that's how it's affected. The scarlet honeycreeper on the island of Hawaii is being pushed to higher and higher elevations because as it warms, mosquitoes can rise to higher elevations. They carry avian flu and other diseases that wipe out any of the scarlet Hawaiian honeycreepers that are still there. So they only survive at elevations where the mosquitoes can't. So species are being affected in all sorts of ways. How many of y'all know pikas? These little guys, you know, they're mouse-like, but they're not mice at all. They are hay farmers. They live on scree slopes next to meadows up in the high altitudes of the mountains. They are very temperature sensitive, so 80 degrees Fahrenheit is lethal to them. They spend their summers collecting vegetation, drying it on the rocks, and building these middens that help them survive over winter. What these maps are showing is basically that as things warm up, these are different emissions scenarios. These red areas will be the only remaining habitat for these pikas if emissions continue in the B1 scenario, A1B scenario, or the A2 scenario. And you can see in the A2 scenario, that's business as usual. If we can continue to emit as we are now, then pikas will be completely gone from the mountains by the year 2100. You are also probably all familiar with the National Audubon Society, a bird watcher society. They have been doing what they call a Christmas bird count since the 1800s. And so a large number of bird watchers go out and they do bird counts in systematic ways. And so they have these huge data sets of where does this species occur and where does that species occur in a particular winter. So they made a blue dot which was the center of gravity for that species in the 1966-67 Christmas bird count. They put a light blue dot, the center of gravity of observations for that species. Then for the winter of 2005-2006, they put a darker blue dot. So you can see for the spruce grouse back in 66-67, that was sort of the center of its range of occurrence. And in 2005-2006, this was the center of gravity of observations of that species. And you can see that some of these species moved more eastward, some of them moved more westward, some of them moved further, some of them less, but every single one of them moved northward, was forced to move northward by the changing temperatures. So we're reshuffling ecological communities. But what happens to that bird if it depends on a particular kind of seed forage or a particular kind of insect food? What happens if it shifts to a new location and what it used to eat isn't there? So we're reshuffling these ecological communities. We don't know entirely what the outcome is going to be, but we expect that it will exacerbate the ongoing global mass extinction of species even further. We're seeing this kind of thing going on here in Flagstaff. How many of y'all are familiar with quadrimundi? Locally, I think they refer to them as quatties. These are in the family Procyonidae, same family as raccoons, but they normally occur in Central America and occurred in southern Arizona up to a point. Now they are up in our canyons along the Mogollon Rim, and in recent years, they've been coming up above the canyon rim into Flagstaff. This is a beautiful quaddy that was treed by some neighborhood dogs in my neighborhood and photographed by my neighbor, Don Caputo. Unfortunately, we're gonna have to skip the ocean effects and go to agricultural productivity. Whew. Wow, I am way behind. So agricultural productivity, of course, is also expected to change as temperatures rise. And we're expected to see lower agricultural productivity in significant portions of the United States, as will be seen in many other parts of the world. And these things are already being seen. So just real quick, drought is a strange thing. Back in 2006, 2007, farmers in southern Minnesota were experiencing drought, yet they had seen an increase in precipitation. Wasn't a great, huge increase, but they'd seen an increase in precipitation. Overall, in the contiguous lower 48 states, we have seen about a 5% increase in precipitation. Yet, in spite of that small increase in precipitation, this is what farmers in Minnesota were experiencing. Again, increased precipitation, yet they were seeing drought conditions. Why would that be? Well, what else is happening? Temperatures were rising in that region, as they are everywhere. And when temperatures rise, evaporation increases exponentially. So even though there's a slight increase in precipitation, there's a huge increase in evaporative loss. And so that's what then ends up resulting in drought. Water availability depends on not just precipitation, but also temperature and wind and soil factors. So all of those things play into this. We've seen major loss of rangeland vegetation in Coconino County, Navajo, and Apache. All these areas in red have seen greater than 80% reduction in plant productivity. As what's shown here is the map as seen in 2018. So 80% reduction relative to the 34-year average prior to that time. And when you talk to the ranchers, what they're seeing primarily, they say we always had spring winds. That's just been a part of the system here always. But now we're seeing fall winds, and that's drying out the range in ways that these plants are not used to. and the ranchers are having to haul more water and more feed in the late fall and winter because of that increase in fall winds and the rising temperatures. So temperature is not rising evenly around the globe. In the higher latitudes, there's actually a faster warming, and part of that is because we're losing the snow cover, the albedo changes, and so those temperatures are rising much more rapidly relative to what was there in the past. We're used to thinking of Iowa as the king of corn, right? And now we're seeing corn productivity in Canada. And this is a story from the Wall Street Journal in 2018 from La Crete, which is in the north part of Alberta, a good bit north from Edmonton. They had seen a 3.6 degree Fahrenheit rise in temperature already. And as a result, they were seeing a steady rise in corn production. Their growing season was lengthening. You can see that's widening as we go forward here. The value of corn growing land in Canada and Alberta has been rising steadily year after year. Each of these histogram bars is the relative worth of that land compared to the previous year. Whereas in the US and in Iowa specifically, we've seen some years where that value of the land has dropped. And those have been years when corn productivity was lower. And so we're seeing that our food production in the United States is shifting northward. And we are going to no longer be the kings of corn production here in the United States. Quickly, a model. These are the projections for all of these major tree species, including ponderosa pine, of what will happen to these species when we reach 2 times CO2 concentration. So if the natural background is 280 parts per million, then 2 times is 560 parts per million. So what happens to ponderosa pine when we reach 560 parts per million? Well, this is the part of the ponderosa pine range that we are in. And it is projected that our entire forest here along the Mogollon Rim is going to be outside of its natural growing conditions when we reach 2 times CO2. Already, Tom Kolb and colleagues tell me that ponderosa pine saplings are no longer being recruited in the lower elevation parts of our ponderosa forest. So this is already taking place. When will we reach 2 times CO2, 560 parts per million? Well, if we continue with business as usual emissions, that will be, when is that about? Well, that's sometime this decade. And we're already seeing those effects playing out. Oh, similar things going on with saguaro and pinyon pine. We won't spend the time, but quickly go to the effects on human populations. Back in 2017, the World Bank came out with a report called Groundswell that projected how are shifts in agriculture and other things going to affect climate migrants. Back then they were projecting that there will be 143 million climate migrants per year by the year 2050. In 2021, they came out with Groundswell Part 2 and raised their projection to 216 million climate migrants per year by 2050. Where are those folks coming from? Latin America, 17 million, South Asia, 40 million, Sub-Saharan Africa, 86 million, and so forth. It's a very detailed study if you all want to take a look. What's going to happen in Central America? Well, water availability is going to decrease. Less so if we rein in our emissions, more so if we don't. That's going to affect agricultural productivity. More so if we don't rein in our emissions, a little bit less if we rein them in. We're already seeing major drought, climate change related drought, intensification and more frequent drought in the northern, what are called the Northern Triangle countries of Guatemala, El Salvador, and Honduras. That's been going on for years already. And we know the result. Those farmers who can no longer support their families because of this drought, first they flee to the cities. If there's not work there, they ultimately flee northward and end up at Arizona's southern border. Okay, so back in 2018, the IPCC report was projecting that we'll reach 1.5 degrees centigrade by about the year 2040. And this is, in this case, this is not emissions on the y-axis. This is actual temperature change. And this is time on the x-axis. So they were projecting, and we based our Flagstaff Climate Action and Adaptation Plan on this projection, that we would reach 1.5 degrees centigrade warming sometime around 2040. The projections have changed. To avoid reaching 1.5 degrees centigrade, we've got to take our rising emissions and reverse them rapidly and dramatically if we want to avoid reaching 1.5 degrees centigrade warming. If we don't, then we will reach basically 3,000 gigatons of CO2 added to our atmosphere sometime around 2050 or so. And we reach 1.5 degrees centigrade warming when we put 2,900 gigatons of CO2 into our atmosphere. How close are we to that? Well, at the emission rate of 59 gigatons per year, it suggests that we've only got, then that was in 2020. We only had 8 years left of putting in CO2 into the atmosphere at that rate, meaning we would reach 1.5 degrees centigrade sometime around 2028. We're now looking at, for the last 3 years, we've been in La Nina conditions. And when we get back into El Nino, which we have this summer, we've already started getting back into El Nino, that in and of itself raises Earth's average temperature by about 0.2 degrees centigrade. We had already raised the Earth's average temperature by 1.3. So chances are, since we're going into El Nino, that we will reach 1.5 degrees centigrade warming sometime next year. When we reach that increased temperature, the IPCC report projects that the annual cost of climate damage will reach about $54 trillion. Does that fit into a global gross domestic product of 149 trillion? I think not. We will not be able to bear the cost of these climate disasters in the very near future. As opposed to, there are folks, engineers from Stanford University, Jacobson et al., put together numbers saying that we could avoid reaching 1.5 degrees. At the time they did this study, the projection was still for being 1.5 in 2040. They were saying that if we spent between 1.6 and 3.8 trillion per year to convert away from fossil fuel burning in all of our energy and consumption systems, that's all it would cost us per year between now and 2040, between now and 2050, earlier projection. And so those are also huge numbers, but those fit into the global economy a lot better than these numbers do. So an ounce of prevention for an unfathomable amount of damage if we don't do it. The effect on global economy. As climate continues to warm, we can expect reductions in global gross domestic product to look something like this, up to the year 2100. If we actually follow the terms of the Paris Agreement, which was made in 2015, then we still going to see some climate change, but not nearly the dramatic effect on global gross domestic product. All these various countries see declines, but some countries actually see increases in projected gross domestic product. Why would a country like Russia if we meet the terms of the Paris Climate Agreement, why would it see an increase in its gross domestic product? Well, remember, agricultural productivity is shifting northward. They have a lot of land that's not currently agriculturally productive, but will become agriculturally productive. And similar projections are made for Canada. Canada is just not on this screen. For China, they're not quite as far north, but why would they see this temporary increase in gross domestic product? Well, if we meet the terms of the Paris Agreement, the entire world is going to be shifting to photovoltaic energy production and wind energy production. And China has situated itself to supply the world with those products. The United States has been selling its patents to China, and they have been falling behind. So we're doing exactly the opposite of what we need to. But China will take at least a short-term advantage from having situated themselves to supply the global shift to renewable energy. As we know, climate change is a multiplier for all sorts of other issues of water scarcity, demographic issues, crop decline, hunger, coastal sea level rise risks, and so forth. If we do nothing, this is the projection that I showed you earlier, but out to the year 2100. So we're approaching present. Present is here. And again, that rate of temperature rise will continue to accelerate if we don't rein in our emissions now. Every bit we emit matters. So what can we do? Well, we need to reduce our carbon footprint in every way we possibly can. And that goes for us as individuals. It goes for our collective carbon footprints. We need to be working with our city governments, our county governments, our state governments, our national governments, and the global footprint needs to be addressed. We need to help species that are being pushed out of their natural habitats through assisted migration. Adaptive restoration ecology is something that's being worked on here by a group of scientists in the Department of Biological Sciences and with the Center for Adaptable Western Landscapes. We need to help those in need because we're talking about a huge societal transition to whole new ways of doing things. What's the combustion engine car mechanic going to do if we don't retrain him or her to work on electric vehicles? So we need to help people in this transition in a wide variety of different ways so that we do not end up with an Earth that looks like this. We need to change things dramatically as fast as we possibly can. So we'll talk more about the potential solutions to this on September 9th. That is next Saturday, same time, similar link. If you go to the nazca.org website, you can see these presentations in the speaker series on the calendar. And if you click on the date, it will take you to a link where you can register for this presentation. I just had to quickly summarize a lot of things today. We'll spend a little bit more time talking about possible solutions next week. Again, that website where you can find the calendar is www.nazca.org. Go to the events, and then any of the calendars will have these presentations since they're Zoom presentations. And if you want to get active with others, please do join the Northern Arizona Climate Change Alliance in your community, and we will empower you in every way we know how to affect change in your community. There are many climate action teams in the different communities. The communities that we are in currently are Flagstaff, Sedona, Cottonwood Verde Valley, and Prescott Quad Cities. So there are active climate teams in each of those communities, and they need your help. Please join them by going to nazca.org/volunteer. All right. Well, with that, thank you all very much for putting up with me for a little over an hour. and I'll be happy to answer questions for as long as you all might be interested.
Stefan, thank you so much for that informative and also frightening presentation. I mean, certainly we could be talking about this for an entire semester, if not an entire year. So I really appreciated all the information you gave us. And, you know, I just got back from Guatemala, and I was interested that in Guatemala, how easily everybody uses the words climate change and how different that is from the US, where we, you know, sometimes even have some concerns about mentioning those very words. So thank you. So let's open it up to questions. There's one easy question here. Where can the Jacobson et al. Report be found?
So it's called this, their publication is about 100-page document that was published in an engineering journal. It's referred to as the Solutions Project, and it was done by Jacobson and colleagues at Stanford, plus a lot of colleagues from the Max Planck Institute in Germany and other places. I do have a copy. If you email me, I can send one to you. And let me put my email address in the chat, so you all can reach out to me directly if you would like a copy of that study.
And Daniel put in information about next week's, the September 9th presentation as well. Other
Thank you,
questions?
Daniel. Yeah, so any questions about any of that? I know this has been kind of a rapid fire summary of many different things. So if any of that was bothering you or you were unsure, have questions, I'm happy to go back through it. If anybody wants to go back through the ocean stuff, we could go back through that too. So anything's fair game.
And Margot, thanks for joining us from London. Can you speak more on how the Schultz fire affects the aquifer recharge rates?
I apologize. I had a whole series of slides in there. So I had to take them out. Just there wasn't enough room in the time we had. Basically, when you remove the vegetation, the water starts flowing much more rapidly and starts to erode the soil. And then lower down on the slope, it forms gullies, and that's where a young lady lost her life, not understanding how deep the water in this particular gully was and getting stuck in a culvert. But because that water runs off the landscape so rapidly, less of it trickles down into the soil, and ultimately less of it trickles down into the aquifer. Now, ultimately, you know, if it runs downhill and ends up in a lake, that could still help to replenish an aquifer. So the details that answer your question are fairly complicated depending on the particular watershed. But in general, it greatly reduces the recharge of the local aquifers because of that rapid runoff.
Thank you. Other questions?
Well, I can't answer everything.
How do we address climate change in a polarized political environment?
Well, that's just it. So that's why I was saying at the beginning, I'm hoping that you all have the interest and the motivation to become climate ambassadors, because we live in a democratic society. And so the more people that understand this, the more likely we will vote for climate aware candidates and affect change that way. Plus, we all have our own personal smaller carbon footprints that we can affect by changing our own behavior. So yes, please do become climate ambassadors. This, as Dr. Reamer mentioned at the beginning, this is the first presentation in a series that we're referring to as Climate Talks for Everyone. This first go round, there will be 2 in a row, that is 1 week apart. But starting after next Saturday, they'll be 2 weeks apart, but they'll all be on the NASCA calendar. So you can always go there to see what's the upcoming presentation. And the presentations are going to range from this kind of basic science understanding of climate change to things like how do you install a heat pump? We have a NASCA climate activist here in Flagstaff who has gotten his house in town completely off the grid. He has stopped burning any kind of fossil fuels. His cars are Teslas. And he has replaced his gas furnaces with heat pumps so he can take advantage of all of the clean electricity that's going to be coming online here in the next year. We have 1,424 megawatts of clean wind and photovoltaic power coming online all around Flagstaff in the immediate future. Right now, we've got the Perrin Ranch wind power plant, which produces 99 megawatts of clean electricity. We've got the Dry Lake Hills wind power plant, which already for years has been producing 127 megawatts of wind power. Babbitt Ranches is putting in 161 megawatt wind power plant just north of the peaks as we speak, and 60 to 80 megawatts of photovoltaic panels. Next year, they're going to start building another 480 megawatt power plant, photovoltaic power plant, also north of the peaks. As we speak, there is a 477 megawatt wind power plant being installed out at Chevelon Butte, which is just the other side of Winslow. And so really, the time to convert to electricity is now because our sources of clean electricity are coming online in a big way. We lost the Navajo generating station, which was a coal burning power plant. And so many of these renewable energy power plants are being put in place to replace the electricity that was being generated from coal. We hope that this trend here is mirrored throughout the world. But, that's up to the people in each jurisdiction. And so in our jurisdiction, we want to make sure that we go as far to net zero as possible. And hope people take that responsibility in each of their parts of the globe.
And hopefully the more people take advantage, the less expensive those options become, right? Because Teslas can still be somewhat expensive, and many of these strategies are costly. So as the more people engage, the more prices will go down.
Absolutely. Yes. As volume increases, price comes down. We've seen that with all of the renewable energies, and wind and photovoltaic solar are currently the cheapest ways on Earth to produce electricity. They beat every form of fossil fuel generation significantly. So for a while, APS was telling us, oh, if we could convert to all these renewables, but your rates are going to go up. Well, they weren't really looking at the big picture. They were just trying to keep us from wanting to push so hard for renewables. It's the cheapest way by far. And we'll talk about that next time. Also, the cost of electric vehicles has been coming down. We'll talk about that. The cost of batteries for EVs has been coming down. There are already several companies in Phoenix that recycle EV batteries. So, there are issues to solve with the EVs, which are lithium mining. We need to do that much more cleanly and carefully than we have. Probably we should be mining our landfills for things like lithium and other rare metals. And I'm sure that will be occurring in the not too distant future. And the prices of EVs have been coming down. So I looked the other day on Carvana. I don't want to promote Carvana necessarily, but there were 8 pages of used EVs for under 15,000. That in part that's because people are they're replacing their old EV with a new EV that has a further range and this and that. Nonetheless, it is not that steep of a hill to get into the EV market these days.
All very positive notes.
So we'll talk a good bit more about that next time,
Great.
next Saturday at 2 o'clock.
Any other questions for Dr. Sommer? Now I have to call you doctor since you keep calling me doctor. So Dr. Sommer, any other questions for Dr. Sommer? There are a couple comments in the chats, but not necessarily questions. So
Right. EV batteries are downcycled for stationary. Okay. So yeah, EV batteries do lose their charge holding capacity over time. And so before they well, when they are no longer so great for for powering a vehicle, they can be used for other applications. And as more and more homes produce their own electricity, we need to look for ways to store that electricity. So using your EV as a storage capacitor for the extra electricity your photovoltaic system produces, that's something that people are beginning to do. And maybe using your weaker EV battery when you have to replace it in your vehicle as a storage unit in your home is probably a good use. So I like that suggestion. Thank you, John. Yeah, and so I think it's Susan Schiff, is that correct? You were talking about BECS and so forth. We will talk a little bit about carbon sequestration next Saturday. So yeah, bring your understanding to that and bring your questions if you have any, or your comments and suggestions.
great. Any other questions? Okay, it looks like we're wrapping up with many thank yous, Dr. Sommer.
Well, thank you all very much for coming, and really do, please, become climate ambassadors. If you've got a way in your own community to do that already, do it with everything you got. If you don't have a way to do it, join NASCA. We'll give you ways. We will empower you in every way we know how.
And support your own passions around climate issues.
That's a good point too. So right now in Flagstaff, we have 14 different climate action teams working on different aspects of Flagstaff's carbon footprint. You still might have something that doesn't fit any of those 14 climate action teams. If that's the case, we hope that you will propose the formation of another climate action team that focuses on that aspect that where you're really passionate about carbon footprint and climate change. So yeah, we're open to new ideas. That's how we get so many climate action teams going.
Well, thank you all for joining us. Remember to check out the NASCA webpage and join us again next week, next Saturday, for Stefan's follow-up presentation on building a path forward. Thank you.
Thank you all for coming.
Thank you, Dr. Sommer.
Yeah. Cannot figure out how